Hello everyone, today we're going to be talking about explainability in AI, especially pre-modeling techniques in modeling and post-modeling approaches that can be used to enhance model explainability. The dataset used in this study contains more than 100,000 real estate property asking prices, as well as 25 different features including location and area of living. Let's start with the data preprocessing. We focused our attention into data cleaning first by removing features with more than 60% null values, as well as eliminating high correlated features and keeping the ones with which had the less number of null values. Additionally, we also removed features like town and city to reduce model complexity later on. We then did the standard train split tests and moved on to handling missing values. In our case, we filled categorical features with the most frequent values, as well as using the median for the numerical ones. For outlier mitigation, we applied the interquartile range method, in which we capped the price values at 1.5 times the IQR below quartile 1 and above quartile 3, preserving the overall data distribution while minimizing the impact of extreme observations. Additionally, to prepare our data for machine learning models, we used one-hot encoding to transform categorical variables, enhancing model performance and interpretability. And lastly, we standardized numerical features using the standard scaler, as well as scaling down the target variable by dividing it by 1,000 to improve numerical stability. Let's now talk about pre-modeling shy techniques. To understand our dataset characteristics, we use Probexity, an open-source data complexity analysis library. And after running the report function, we can clearly see three main complexity scores. The high S2 score, which measures feature similarity for instances with similar outputs. The T2 score, which evaluates decision boundary complexity. And the C1 score, which assesses dataset sparsity. All these feature scores suggest that we need advanced and non-linear modeling techniques to understand our data. Additionally, we also use different dimensionality reduction techniques in order to try to explain our data. We started by running principal component analysis, and we can see that on the one-hot encoded data, the PCA can clearly make a gradient using the price values, whilst the one without the one-hot, we can really make out any clusters or relations. Lastly, we use t-distributed stochastic neighbor embeddings to try and understand the data distribution, and on this case it's a little bit more complicated compared to the PCA, and both approaches seem to not be able to cluster the dataset correctly.
Going into the in-modeling approaches, it is most known that decision trees are among the most common models when it comes to interpretable machine learning, as they are a rule-based kind of model, which has usually a clear visualization of the decision process. As a baseline, we decided to create a model with our data, with any kind of depth and ramification factor, and seen as in this image, you can see that our decision tree, although it is a decision tree that is supposedly explainable, it is not really interpretable. It has a depth of 10 and a branch factor of 2, which makes all the rules extremely complex and lengthy, and it's not really interpretable for a normal person. It has the following metric values: root mean squared error of 162.67 and a R-square correlation of 0.6, which indicates that the decision tree does in fact manage to successfully explain the data, but as said previously, it's not really explainable. So we decided to, through the feature importance, select only the top 5 most important features in order to create a sub-data set with only those features and try to reduce the size of the decision tree. And through that, we made 5 depth decision tree with a branch factor of 2. It has much simpler rules and it's much easier to interpret, but the overall performance slightly lowered. We believe that this lowering of performance, as expected as it is, it's a trade-off we should probably make, given that it's much preferred to have an explainable model with a little worse performance at a baseline model with a little better performance but extremely complex and not interpretable rules. Going over the post-modeling approaches, we had to develop three different kinds of approaches, and we're going to begin with the simplification based technique. For this technique, we chose surrogate explainability, which is based on the idea that training an interpretable surrogate based on the predictions of a black box model allows us to explain the decisions of a black box model. So, uh, we developed a multi-layer perceptor network with 3 layers, and it had a root mean squared error of 153 and an R-squared correlation of 0.63. We passed the test data through the neural network, and we created a new dataset replacing the original predictions of each row with the predictions of the neural network in each row, and then we did a train test split on that data to train the decision tree that was going to be used as a surrogate model in order to explain it. So, training it, we got 3 with the following metrics. On the predictions of the neural network, it had a root mean squared error of 125, which is really good, and a similar R-squared correlation, which is not unexpected, but compared with the real data, it had a much higher root mean squared error and a much lower correlation, which is also unexpected. Although it had these values on real data, its main objective is to be compared with the predictions of the neural network, which will imply that that surrogate model is able to confidently explain how the neural network works. So, given this, we managed to create a surrogate model that successfully explains how the neural network decides. Now going over to feature-based techniques, we will use tools like SHAP and Lime to identify and analyze features that contribute the most for the model's prediction. In this project, we used SHAP and Lime in order to generate global explanations and local explanations, respectively. Going over the global explanations, we used our previous neural network model with SHAP, and we ran 1000 samples of the data we had through it to generate global explanations. For instance, we can see that features like the number of bathrooms and that Lisboa usually have the most impact on the model's predictions, which in this case means that the more bathrooms we have, or most of the samples in Lisboa had an enormous increase in price. And similarly, we can also see that living area and total area also do contribute a lot into the price increase. Then going over local explanations, we can see that we can't visualize all the testing we've done because Lime only works for a single sample instance and it's a local explanation. So the explanations will vary a lot, but through the testing we did, we can see that generally Lime revealed that the parking options of a real estate, the construction year, and the energy certification the real estate had a strong influence on the behavior of the model, and also that Lime placed much more emphasis on the binary features of the dataset instead of the more linear ones, the numerical ones.
As an example-based technique, we decided to implement counterfactuals for model interpretability. Counterfactual explanations consist in describing the minimum changes required in an input to achieve an alternative decision outcome. We used as a base a linear regression model, and to generate the counterfactual explanations, we used diverse counterfactual explanations, or DICE for short. The framework was configured to identify what changes would disturb the housing pricings within a range of €10,000. We applied the DICE model to both a small sample of instances and a random batch of 1,000 in order to visualize the feature adjustments. We then visualized the data using gradient graphs to better understand the changes across features. The x-axis represents the value of the feature, the y-axis the frequency of that value, and the color gradient in the line represents the changing of average pricing, from red representing low average price to blue which represents high average price. As expected, many counterfactuals were generated through the manipulation of the construction year and number of bathrooms. And the features like living and total area need a high different value to influence the pricing, whilst number of bathrooms take much less effort to change the pricing of housing. Various examples show that alternating the building type, residential, commercial, or office, influences the overall housing price in a high degree, which show that buildings of similar fashion have different market values depending on their purpose. To qualify the explanation, we chose to analyze the circuit model used in the simplification-based technique using three different metrics: accuracy, fidelity, and stability. Accuracy consists in the rate of correct predictions that the explanation makes using real data. Fidelity consists in how accurately the explanation matches the black box model's predictions. In some instances, this can be interchangeable, as an accurate explanation reflects an accurate black box model. However, in the cases where the model's accuracy is low accuracy in the explanation is a better reflection of the models and conveys higher fidelity. The accuracy and fidelity of the circuit model can be obtained by comparing the prediction values of the explanation with both real data and predictions of the black box model. What we can see is that even though the accuracy is low, the fidelity with the black box model is high, which indicates that the explanation is a good reflection of the model and that it has low accuracy. The stability measures if slight variations in the features of an instance substantially change the explanation. We can calculate these values by introducing Gaussian noise to the test data and see the difference between the feature contributions of the explanation when predicting using the clean and noisy data. What we calculated was that it was necessary to introduce a high value of standard deviation in the noise in order to see significant differences in the feature contributions. This shows that the explanation is stable. With the knowledge that the explanation has low accuracy like the model, presents a high degree of fidelity, and it is stable, we can say the explanation is a good reflection of the black box model.